Very good afternoon, and would like to congratulate the team which is organizing this Techniche. It's a great feeling to have seen some of the good innovations done by young and middle-aged and the college students. Being in IIT Guwahati, I feel very happy because it was about 5 to 6 years back when I came here and visited the biotechnology department and the Department of Mechanical Engineering. I was that day itself impressed by the kind of work which is being done in this institution. So when this offer came that I should talk to you, I thought the best way to interact with you is to give the glimpses of what the country needs and how the technology is emerging and that how this technology can be made use of for meeting the needs of the nation, humanity as a whole. And as all of you know, the technology is going through transformation. What used to be once upon a time a standalone system, today it's the convergence. These are the days of convergence, and diversity and convergence are the two buzzwords which are actually taking us from what we were about 100 years back and what we would be in the next 50 years to come. So my topic is that we talk about the frontiers of engineering, and we would like to share with you some of the civilian aspects and also a bit of what the Army and the Air Force and the Navy would be needing or doing based upon the technologies what are emerging today. All of you know that we live in a world shaped by engineering. We know whatever is happening around us, whatever comforts we have, we are making use of are the fruits of engineering, and it has brought us all kinds of comforts. It has made people happy. It has made people safe, and also it's a symbol of progress. So, as somebody said, it surrounds us, it connects human society and engineering creativity that designs the world we want and turns ideas into reality. Basically, it is the overlap of the scientific knowledge with the technical, with the societal needs and application of scientific knowledge to the needs of the society. And this is one thing which I would like to mention to you, that when I joined NITI Aayog, within about 3 months, our Honorable Prime Minister had a meeting with the large number of very senior scientists of this country. And there was professors from IITs, there were academicians from other institutions, there were scientists from national laboratories. And only one message he delivered on that day. He said, for the last about 70 years of independence, I have seen the growth of, or in this case, I'm quoting Prime Minister, I have seen the growth of science in an individualistic manner. There are very, very acclaimed scientists who have made name worldwide. They have done wonderful work. But I would like you to now start doing work for the society. That means he gave a focus that we should go to translational research, do more and more innovation, commercialization, and be a succor or be a relief mechanism as far as the country's needs are concerned. So this is what the definition, and this is what the world has done so far. It is also seen that over the centuries, right from the 5000 BC till today, when we grew up from Stone Age to the Bronze Age to the Iron Age, then Chemical Age and Plastic Age, and today we are in an age of information, knowledge and technology. We have really made wonderful progress, the society as a whole, the human beings as a whole. And it used to be an agri society. Today we are an industrial society, and we are also graduating into an information and knowledge society. Now, you have seen things right in front of you, those of you who have visited some of the things which were realized in say 912 BC, they still exist. And now Tipu's rockets, what you have seen, which came up in 1792. And then we had the Industrial Revolution, which staged a complete technological scenario as far as the world is concerned, which brought in certain amount of human labor getting converted through machines, and machines converting into mechanisms which are going to be more and more efficient, and hence the technology became the building block for the happiness of the nation, of the world as a whole. Now, from there, we got into nuclear energy, we got into today DNA, and we have got carbon nanotubes coming in. And today we have revolution in the HMI through molecular nanotechnology. I saw some wonderful work being done in this area on biomolecular subjects. So basically it's an emergence of smart and intelligent systems and materials which is taking place in the 21st century. It is technology of nano age which is driving the entire thing. So this transformation which has taken place over the last maybe say 1,000 years, and what we can reckon with, and that is what is going to now pave way for the next generation of things which will happen. We have seen in India, in just last about 70 years since independence, I am quoting, what has India achieved? You know White Revolution, you know Dr. Kurian who was responsible for it, and that's why we are the largest, first nation in the world, first country in the world which is doing the largest production of the milk products. We had our Green Revolution which is responsible for today's food needs of the country, to the extent that we have surplus food stocks today, and that was the first Green Revolution. Person who was responsible was M.S. Swaminathan. You have a huge ICT scenario, the information communication technology scenario. Dr. Kalam's space and defense ventures had led to satellites, missiles, armaments, and variety of missions, including Chandrayaan and Mangalyaan and all that. We today have an indigenous aircraft carrier. Today we have indigenous submarine, INS Arihant. Today we have nuclear power plants in the country, and we have huge railway networks which is available. So you see the way the technological growth has taken place in the country, making use of what has happened across the world during the during the Industrial Revolution, and doing our own value addition, ensuring that we have certain amount of self-sufficiency as far as these things are concerned. And generally on the earth, the engineering contributions are on the earth, water, air, plants and animals. All of them have either in the form of dams or in the form of river control or in the aircrafts or helicopters or windmills or the agriculture methods. Basically they are responsible for the growth of mankind's requirements and the needs being fulfilled. Indian engineering for the changing society. There are success stories, as I mentioned to you, across agriculture, telecom, ICT, space, defense, pharma. And today we have the biggest advantage. We call it 3D advantage. And I saw the 3D advantage today when I saw the youngsters doing wonderful work. We are the largest democracy, that is the first D. We have a demographic dividend because our 60% of the population is in the age bracket of about 24 to 35 years, which has got strong domestic demand because we are large number, 1.3 billion people. So domestic demand is that these three Ds are going to drive what we call as the major strength, or what are the major market demand which will come on. Now in this process we have researchers which are deploying technologies emanating from applied research areas such as bio-inspired engineering, biomimicking, brain-machine interface to critical areas like health and hygiene and food and agriculture. These are the new disciplines which are actually changing the scenario altogether. But in spite of all that, today we need to really direct our energies to solve the problem of poverty, because 1/4 of our Indian population is under below the poverty line, and 70% of them live in the rural areas. Women population is also about 46%. Now in this case, empowerment of women, taking care of people at the bottom of the pyramid and bringing succor to the people who really need things, and hence we have to do what we call a strive for, I mentioned in the inaugural also, innovation and solutions that are pro-poor and address the needs of the society at the bottom of the pyramid. That is what we need. Now where do we stand? As a nation who has been now independent for last 70 plus years, where do we stand with respect to the global comparisons? India ranks 40 in travel and tourism competitive index out of 136 countries. India ranks 60th in the inclusive development index. These are all numbers which will tell you where do you stand with respect to each of these factors. 87 among the 127 countries in the energy architecture performance index. Then we rank 20th out of 58 in the climate change performance index. We ranked 92 in the global index of talent competitiveness, INSEAD as we call it. India ranks 143rd in the economic freedom index out of the 186 countries. India ranks 43rd among the 45 nations in international intellectual property index. That means how many of us are in a position to get the real IPs. 9th in the bribery and corruption in business. That's the only area where we are up in within 10. India ranks 79 out of the 176 countries in corruption perception index for the year 2016. 131 in 2016 on what we call the human development index, and that's one of the very important parameters, because that gives you a real picture of how, in terms of education, health, employment and other aspects, how we have developed in development index. So you see, where do we go? Where do we stand in this? As a result, with this kind of our standing today, we have a major journey to perform, and we have problems in front of us. We have commitments which we have made on the international platforms like COP21. So that is where, who will solve the big problems? Now that's where we are in IITs, we are among the youngsters, and the problems are, for example, sustainable development and climate change. We have a requirement of clean water. I saw some kids doing some wonderful work in cleaning technologies for cleaning water and so on. Population and resources. We have ever increasing population. We have to match the resources with the population demands and so on. We have a situation where we are a democratic country where democratization is a major issue. But democracy with accountability and responsibility is what is to be imbibed in. Not democracy purely with respect to what is thought of as freedom to speak and freedom to act. Global foresight in decision making. While we are making decisions, it is important for us to take what the global needs are there. We just saw the indices which I mentioned to you. They are also indications of where do we stand globally. So when we make decisions, global indices, global foresight has to be kept in front of us. Global convergence of IT, rich-poor gap has to be filled. There are large number of health issues. There are what is our maternity rate and what is our nutrition rate. We know about about 44 children out of 1,000 are malnutrition. That is a kind of number. So we have huge health issues. We have education issues because in spite of the fact that we have some of the best policies to promote education, we still have people, dropout rates are how, GER are not very good. So these are the issues to be handled. We have our own problems of peace and conflict, internal as well as external. Status of women, our Honorable Prime Minister has been literally fighting for it, that we empower our women and give them equal status, if not better, as far as the society is concerned. Transformational organizational crime, transnational organized crime, this is another problem. Energy needs, because energy is one indicator which gives you an indication of what is the growth of the nation, what is the development indices. For example, a developed nation will consume something like 5,000 to 5,500 kilowatt hours per person per year. Whereas in India, we are still at about 1,075 kilowatt hours per person per year. So that is a kind of difference. That also shows the difference in the development activities. Science and technology is a major indication, major actually vehicle for growth, and hence that has to be taken forward. One thing which we saw corruption indices and all such. Global ethics is what is another problem which we have to bear with. Now all this can be solved by graduates who are highly creative with bright ideas, and that's why this slide for all of you. These are the challenges which we need to really take into account. Now, as the technology is going to come, the future dangers are worse than the most optimists indicate. There could be things, while we have nanoparticles, we have nanotechnologies, but there are issues with nano. While we have got tissues which can be, organs which can be artificially built, but there are issues for them. For example, advanced technologies could lead to global long-term structural unemployment. We are all saying artificial intelligence, automation, robotics, and self-driving cars and so on and so forth. But all this will lead to what amount of Industry 4.0. Is it going to take away the work of a large number of artisans and masons who are really working in the industrial area? Has anybody thought? One analysis which has been done by the FICCI, which says that if we employ Industry 4.0, 69% unemployment will come up. Of course, I don't agree with that number, because I personally believe that it won't be unemployment, but it will be basically a different kind of a job profile that will emerge. And hence we have to actually skill our people to meet those requirements. Individual could only one day make and deploy weapons of mass destruction. Today, nuclear technology is so well known. Artificial intelligence could evolve beyond our control in a destructive fashion. We can read the mind of the people. The cognition is going to be so strong that we can use that information for destructive purpose. Proliferation of advanced destructive weapons among the hate groups, long-term effects of global warming, organized crime leaked to the world like Central America condition, all this. Urban infrastructures may become too complex to manage, maintain and prevent sabotage. It is already happening. You see the major metropolitan cities today, the urban infrastructure has become so complex that managing it both in terms of human population, movement, pollution, energy needs, food supplies, all that is becoming very, very complex. And as the numbers are increasing, urbanization is growing. As I speak to you for 1 minute, 33 people walk into a city like Delhi in 1 minute, as we discuss, from the rural areas to urban areas. If that is the rate at which 50% of the population of India will live by 2035 or 50 in the city areas. Somebody says that urbanization is the indication of growth, because it's true also, because if you see the contribution of the urban population versus the rural population, 33% population which lives in the urban areas contributes 66% to the GDP growth, and whereas the balance is from the rural areas. So that is an indication of growth also. But then you have issues of urbanization. Large enough asteroid could hit the earth and cause nuclear winter. Doomsday scenarios of nuclear proliferation are possible. These are some of the things. So the greatest challenge as far as the 21st century engineering is concerned is global sustainability. We need to ensure that we are taking care of all the three pillars of sustainability, namely the social pillar, the economic pillar and the environmental pillar. Unless we take care of that and every decision which we take passes through the lens of sustainability, we will not be doing justice as an engineer. And that's why today, if you look at, to meet the sustainability goals, which many of you might have studied both with respect to poverty, hunger, health, quality of education, gender, variety, these 17 numbers are there, all of you must have read that. If we had to meet all that, we had to change our system, and that system is global system, social system and human system. Global system means climate, resource, energy, ecosystem will lead to global sustainability. Global warming will certainly, if it is there, then we have to go for low carbon society. Mass production, consumption and destruction, if we go away from that, we will get sustainable production and consumption. And poverty, natural disasters and infectious diseases, if we can get rid of, then we get a human security. Now all this has to be done as part of the sustainability development program. For that, the engineering has to transform itself. Why I am giving this indication? Because whatever we are doing today, or the people of my generation have done, we have concentrated on traditional engineering practice in which we consider only an object and we design an object, make it useful, and that's the end of it. Whereas today's engineer has to consider a complete system in which the object will be used. We used to focus on technical issues. We never bothered about social issues, non-technical issues. But today we have to integrate any engineering decision, it has to integrate technical and non-technical. We used to solve immediate problem. There is a requirement for a bridge to be laid, we will say the bridge. No. We have to solve the problem for indefinite future, forever. We should ensure that the problem completely disappears. Considers the local context. We have always bothered about what happens with the vicinity. But we have to look at a planet as a whole. If what I am doing today in the city of Guwahati, if it has impact on somewhere else, then we have to be worried about. Assumes others will deal with politics, ethics and social issues. We never bothered about it. That was a good interlude. Let's go from what we were discussing, the sustainability that is essential for tomorrow's survival. That means basically we are looking for leaving this planet for the future generations, and engineering has to play a major role. And that's why future manufacturing will be where you look for cleaner, advanced materials, manufacturing technologies to grow India's future productivity. Then we have food futures, where we have flagship will transform the agri-food sector of the nation through new technologies. I don't know how many of you have ever studied what did the first green revolution do. While we have a high productivity in the first green revolution, but there are negative impacts of that in terms of excessive use of the groundwater, excessive use of pesticides, and also the fertilizers, leading to the soil becoming non-usable and so on. And there are issues with respect to pollution of water. Biosecurity is a major requirement, where threats and risks posed by the serious exotic and endemic pests. Preventive health, as I mentioned to you, we are a society where we have maternity, mothers' survival rate, children's problem, nutrition, all of them. We have sustainable agriculture, which we have to reduce the carbon footprint, so that has to be done as part of the global. Water for a healthy country. Water is going to be the major problem in the nation. So we have to look for sustainable management of India's water resources. Climate adaptation, as all of you know, we have signed COP21, and where we have said that we will reduce our emissions to a large extent, 30% reduction by 2030 or something, which is a major commitment we have made. So we have to bring that part. Wealth from oceans, that is one area where we have not done enough. We have huge wealth available in the oceans, and we have not exploited. So science and technology has to look at that. Enduring social, environment, and economic wealth from the vast ocean territory. Energy transform, we are getting into renewable energy in a big way today. We have known goals, 175 gigawatts and so on, solar and renewables and things like that, which have to be done. Minerals also, delivering science and technology solutions to the Indian mineral industry. And as I was mentioning to you, we have to take care of our people at the bottom of the pyramid, which is the user community pyramid shown here in the bottom. And right from the sea, land, river, information collection about all of them, remote sensing through satellites, GPS through navigation, data center and cloud computing and network, all put together to make sure that the geospatial technologies are harnessed to bring sustainable development for rural areas, urban areas, fishing community, farmers, industry, and the government. That is the demand. That's why those who are in the manufacturing today, the transformation would be from what you are having traditional manufacturing, where you used to do manufacturing through substitution. Then we turn to lean manufacturing, where our focus was waste reduction. Then we turned into green manufacturing, where we were combining that, ensuring that the energy is minimized, economically used, and environmentally benign. We used to call it 3R based approach in those days. And now we have gone into sustainable manufacturing, which will be innovative, and it has got what we call as a 6R culture. What is the 6R there? Remanufacture, redesign, recover, recycle, reuse, and reduce. This is the kind of cycle, and it will also lead to what we normally talk these days, circular economy, and that will meet the requirement by 2050 that we have minimum wastage, minimum utilization of resources for meeting all the demands of the nation, and that is the sustainable manufacturing which we are talking of. So, in terms of challenges, as others see, grand challenges for engineering are make solar energy economical. It's already happening today, but it is happening at what the Chinese are able to do. We are able to make our solar energy cheaper because we have cheaper solar cells available from China. We have not done enough ourselves to make sure that our solar cells are quality and quantity and cost-wise competitive. Provide energy from fusion. This is one area we have neglected. Develop carbon sequestration methods to reduce the carbon footprint. Manage the nitrogen cycle better for better productivity. Provide access to clean water. Restore and improve urban infrastructure. Advance health informatics, because unless we are able to get the entire information about what is happening to each and every child in the village, to a mother who is pregnant, to a guy who is old, we will not be able to provide the health system as far as the nation is concerned. Engineer better medicines, reverse engineer the brain. This is another challenge. Prevent nuclear terror, secure cyberspace. This is another area which needs our immediate attention. Enhance virtual reality and advanced personalizing. The learning should be personalized. Engineer the tools of scientific discovery. If we do that, then the right side what is given is the Millennium Development Goals, which have today become the Sustainability Development Goals, will get solved, which will be able to reduce child mortality, improve maternal health, combat diseases like HIV, AIDS, malaria and others, ensure environmental sustainability. All this will happen. Biology and engineering can effectively address these challenges and create significant societal impact, and that's what is happening. Where are you with respect to innovation today? We are in the sixth wave of innovation, because the first wave starting from 1785 to the wave in which all of us have lived through is the petrochemical and electronics. That was the fourth wave, which we have seen it growing. Overuse of crude even today happens. Then we have seen between 80s and today the digital network, biotechnologies, software, information technology. But what is happening today is sustainability, radical resource productivity, whole system design, biomimicry, green chemistry, industrial ecology, renewable energy and green nanotechnology. This is what the innovation wave is driving today. And for that innovation wave, the technologies which are coming up, which are, we call them as the transformer or disruptive or transformative technologies, because they are significant, they make potential for significant systematic, economic and political impact by boosting industry productivity and competitiveness. They enable us to address long-standing problems and global challenges, and have the potential to create new industries and manufacturing opportunities, can provide sustainable, high-quality, high-wage jobs. And these technologies, many of you have already started using them. ICT is well known, which is really going to transform the entire situation. Biotechnology, nanotechnology, genomics, microelectronics, advanced materials, and remote sensing, GIS using 3D LiDAR, high performance computing and analytics, instrumentation and control, mathematical modeling, isotope marking, 3D printing, additive manufacturing. Some of them only I have listed, the list is pretty large. Nanotechnology, which is really making the difference. The grand challenges by the foundation, Science Foundation has identified, is nanostructured material by design. The ability to measure, control and restructure matter at the nanoscale in order to change those properties and functions as we need. Nanoscale electronics, smaller, faster, cheaper computers and electronics. Nano manufacturing, nanotechnologies to improve the environment, and nanotechnology to improve the healthcare, where nanotech inspired medicines and treatments are there. In fact, I was discussing in the morning with your director sahab, where he was telling me how the drug can reach at the right place in the right quantity using the nano particles and the methods of microfluidics and so on. Very important. Future technologies where the synergies are taking place: synthetic biology, robotic manufacturing, quantum computing, drones, robotic manufacturing, 3D, 4D printing, augmented reality, telepresence, nanotechnology, tele everything, tele every day, and tele everybody. This is the kind of thinking. Artificial intelligence, and this is not just artificial intelligence. Now it is getting a different name, artificial general intelligence, and increasing individual and collective intelligence levels. Now all these technologies have to work in a synergistic mode to solve the problems, and that is where the technology change is taking place. Bioengineering is one thing which is really important, because it is bringing everything together. For example, in a bioengineering, you have chemical engineering, you have mechanical engineering, material science and engineering, electrical engineering, physics, chemistry and biochemistry, biology and neurobiology, computer science and engineering, all put together to meet the requirements of food, agriculture, healthcare, clothing, aerospace, shelter, energy and chemical. All this is part of the highly interdisciplinary this science is becoming, and that's why it is becoming more and more important that engineers have to learn biology in a big way. I hope IIT Guwahati is also running some courses of biology for the engineers in some way. I saw it is happening in IIT Delhi. I hope you are also doing. Bio-inspired engineering addresses the unmet challenges, making a difference to the world. Richly collaborative and smart therapies, biocompatible implants, 3D printed organs, engineered heart cells and so on. This is all becoming part of that. And also most important thing which is coming out is the biosensors. And today in the smart systems, biosensors are going to play a major role. We have a major demand. I mentioned to you about how to reduce the cost of energy, particularly solar energy, which is dependent on what is the cost of the solar cell. It has been tremendous activity throughout the last about 2 decades when people have been working on reducing the cost of solar power, and started with organic solar, quantum dot, then you have concentrators, amorphous silicon, cadmium telluride, then polycrystalline, multicrystalline, monocrystalline cells, all of them. The goal post is that we should be somewhere close to about 0.2 to 0.1 or $0.2 per unit, that kind of a thing. Greatest cost reduction is expected. That will happen only if we have highly efficient systems. So multi-junction solar cells are what people have been working on, which requires tremendous amount of R&D even today. The left hand side here you can see there is already a combination in multi-junction solar cells where you have gallium and phosphide and gallium arsenide and germanium, which gives you an efficiency of 38.7. There are combinations which will give you 42. There are other combinations which can give you as high as 43.5. Gallium, indium, and arsenic, antimonide, all this can, some of these new combinations can give. There's a lot of work which is going on abroad. I have visited number of IITs, number of NITs, number of places, but unfortunately group 3-5 materials, not much work in India has been taken up. I would certainly like to know if somebody is really doing good work here, because we know that theoretically you can get as high as 45% efficiency, but to get the process of manufacturing in such a manner, because this is not the same process as we have in the photovoltaic cells today. This is a different process where you have molecular epitaxy and things like that. But this should also bring down the cost. This is a major area. Another major requirement is hydrogen economy. Hydrogen economy is what we have to see as far as the energy is concerned. And it would need, how do you extract hydrogen efficiently, how do you store hydrogen efficiently, and how do you transport hydrogen efficiently. And then you have a fuel cell which is cheaper compared to the today's IC engines. That means I should be able to produce hydrogen using coal, nuclear energy, solar, wind, thermal, and all that. That electricity heat which decomposes, electrolyzes water to give hydrogen, and then I should combust the hydrogen to give either a hydrogen engine, or I use it in the fuel cell to generate electricity. The advantage is that you have only water vapor as the effluent. Now, what is the situation with respect to hydrogen? Whatever research has been done so far, if you see the current technology for automotive applications, what is the current gravimetric energy density, that is the millijoules per kg system. At the left hand corner you see all of them piling up there, chemical hydride, compressed gas, hydrogen, and so on. Liquid hydrogen is also very close to that. And you see the rightmost corner, the gasoline which is sitting there, which is the today's fuel. We are nowhere near what the gasoline can do. So unless we are able to get freedom, what we call as 4.58% of hydrogen by 2005, that was the goal set in 2002, to 9% weight hydrogen by 2015, we are nowhere near even then. So there is a huge research requirement for hydrogen storage. Same thing is going to happen in the areas of CMOS, which is a communication technology which is becoming. You have seen the 28 FD, you have got 14 FD, you have got 10 FD, and in 2009 we were all talking about 28 nanometer, but today we are all in 5 nanometer, 7 nanometer, and 2025 you will have single electron transistor, 2D materials, neuromorphic architectures, and big work which is going on in quantum computing. So these are disruptive scaling technologies which are coming up today, and memories are getting 3D and so on. So this is one area which needs our attention. Group 3-5 transistors is another area which will be needing our attention rather than continuing with the silicon. So this is the advanced CMOS roadmap which we have. The main thing which is going to happen is the microelectronics getting integrated with the photonics. And this diagram shows you how an arrayed LD or memory or a many-core CPU with a silicon optical interposer can have a silicon modulator, photodetector, waveguide, PCB, or a BGA which can be attached to that. The idea is that you have processor interconnection, multi-core to many-core, memory interconnection, which is flat memory to 3D memory. We have a storage interconnection with SGD to 3D SGG, peripheral interconnections, HDMI to super high vision, and server interactions, which is exascale computing. This is what is going to happen, and you can see on the left hand side, you have the complete on a 2-inch with a photonics layer. The 3 types of layered sandwich structures are feasible for the implementation of integration of photonics and electronic circuits. Front-end integration, back-end integration, and flip chip bonding. The first two are monolithic integrators, and the third is a hybrid integration. I have been trying to propose this kind of a work in many of the institutions today, because I personally believe that the distinct advantage which is there in this has to be tapped if we have to really go for hexascale computing and so on, which is the major requirement for HPC today. We saw evolution of teraflop computers between 1999 to 2009. 10 to 20 is a technology changer leading to the exaflop computing. So we have large-scale hybrid architectures which may evolve further, but power consumption is a major issue even today. We need megawatts of power for doing exascale computing. So we need power-efficient processing cores, optical system interconnect, as I mentioned to you, efficient interconnection topology, nanoscale memories, and highly scalable programming environment and parallel libraries. That is the requirement for the high performance computing. I am also looking after this as a chairman of the Empowered Committee for High Performance Computing Program of the Department of Science and Technology and the MITI. We are struggling to get that we can have some of these technologies done in our country, otherwise most of it is imported. You see this optically interconnected system. You have an integrated silicon photonics processor, then there's a multi-chip module, then there's a board, array of boards putting in a rack, and you create a data center. Now you see the size difference. A shipping container will have a big data application, a pair of photonic computer which come in a suitcase size. The difference will be, weight will be, in the case of Photonics VCM2, it will be 19, so sorry, almost about 19 kg, whereas IBM PUX weighs about 6,000 kgs. So that is a kind of difference. Power consumption will come down to 5 as against 902 kilowatts. So this is the kind of change that can take place if we really go into this. The future technologies which are coming in these areas are tunnel FETs, graphene PN junctions, orbitronic, domain wall logic, spin FET, spintronic majority, spin wave devices. I feel these are the technologies which are going to drive tomorrow, and if we have to really go into the next generation of microelectronics to solve the problem. Quantum computing is one area. We have a quantum annealer, 3 systems are there. Annealer does not give you any great advantage because the speed wise is almost the same. Whereas quantum analog computing, likely form of quantum computing, that will first show the quantum speed up over the conventional computing. Here you have almost about 100 qubits. That is the kind of configuration you have, and generally it is it is power wise it consumes high power. But the third one is the universal computing, where you will have almost about 10,000 qubits kind of a thing. True grand challenge in computing areas with the potential to be exponentially faster than the traditional computer for a number of important applications, and that is what we need to develop. The world is going to see IoT explosion in a big way. All of you know this IoT, we'll skip that. So applications which are really going to be affected by IoT are home building, transportation, logistics, smart industry, small retail, smart environment, precision agriculture, health. Some of the projects which some of the boys and girls have shown are certainly useful precision agriculture, where you can deliver the right amount of moisture, the right amount of fertilizer, and seeding and cutting and so on. All this is feasible today. For example, in transportation, you can do with IoT traffic management, congestion control, connected cars, smart roads, and so on. In the case of home and building, you can do monitoring and control of internal building environment. In the case of health, certainly you can do monitoring of the medical health of the system and so on. So the Internet of Things is going to drive the entire scenario in future, and that's why cyber physical systems are becoming more and more important. But even in the cyber systems, physical was a steam engine. Today's systems, what we saw are the telecommunication, computers, internet. But physical and digital context, cognitive revolution is going to take place with augmented reality, virtual reality, and service robots, IoT, 3D printing, and even 4D printing is coming up now. So we have smartness coming in everywhere. You will have smart cities, and smart cities means they will be leading to intelligent nation. While smart cities means smart business, smart environment, smart mobility, smart utility, smart infrastructure, smart government, smart citizens, and smart education. All of them are part of the smart and intelligent technology scenario. The thing which is going to change the complete communication scenario in the next 5 years, and it's already happening in many cases, is the 5G. 5G is going to drive the entire process. For example, if you take the advantages, ultra low complexity, tens of bits per second, ultra high density, 1 million nodes per kilometer square, extreme capacity, 10 terabytes per kilometer square, extreme data rates where multi-Gbps peak rates of 100 plus Mbps user experimental rates can, ultra high reliability, that is what is going to 5G's revolution. 1 out of 100 million packets will be lost. Ultra low latency as low as 1 millisecond, and strong security in terms of all the requirements with the and particularly in the health area, education area, financial securities and so on. So mission critical control, massive Internet of Things and enhanced mobile broadband is what the 5G is going to bring. So there's a need for us to get more and more technologies developed in-house in the country on the 5G area. Another one is the intelligent grids. We just saw power failure. Now, integrated and intelligent electricity system of the future, where you have storage devices like pump hydro, compressed air, batteries and so on. We have smart transmission and distribution networks, we have smart energy control systems and smart users like the local grids and the micro grids which are formed due to rooftop solar or the wind, local wind and so on, all put together on a distributed energy resource management system. To integrate all elements of electricity system will increase complexity, but improve operations, efficiency and resilience while optimizing energy resource and investment. Recently only we had a workshop on this smart grids, and we found that India, if it has to look at smart grids, both AC and DC, we have to make a lot of technological change with respect to the power electronics, with respect to our distribution sensors, and with respect to our computer data analytics and big data approach. We have to do that. And that's where big data analytics comes, because that is going to drive clean energy, advanced manufacturing, everywhere. Big data analytics is going to be the major requirement as far as smart and intelligent systems are concerned. Whether they are sustainable energy or microelectronics, data is going to be responsible for improving each one of them. Clusters benefiting due to big data are all given in this, they are in the red indicated here. So big data analysis, big data mining, data analytics are the important areas which all of us have to work for. 2025 will see robots have entered our homes for personal use. Sensory devices guide our everyday lives. And mobile financial transactions are now in cryptocurrencies. It is likely to happen. There are 6 million autonomous cars in Europe and North America. This is what the prediction is. Big data has entered the gigabyte era. The 3D and 4D printing is gaining mainstream acceptance. High-speed rail to connect from China to Europe. And summer, say, low-cost holidays in space. That is going to be something which is predicted by 2025 due to the frontiers of technologies which are evolving today. A few things I would like to show on the defense, because I am a defense guy. You have to certainly know what the technologies are going to do as far as defense is concerned. The warfare is going to change. We are going to change into what is called non-contact warfare. Because we have today information domain, where we collect information, we have cognitive and the social domain, and we have physical domain which controls the weapons and so on. And all that are on a network. So that's why it is called network-centric warfare these days. When we have the disruptive technologies to create theater and battle space, what are those? Like cyber warfare, it is disruptive. Anti-satellite weapons, underwater warfare. I saw some underwater ROVs being done by the kids here. Directed energy weapons, and that is what's more important. Directed energy weapons means I don't come in contact. I send a particle beam, a laser beam, and finish off the enemy's objects. So contactless wars, missile warfare, submarine warfare, directed energy weapons, and space control weapons. The satellites what I have may be carrying the weapons, and they may be carrying certain things which are not good for us. So we have major issues as far as this is concerned. So this is a new warfare perspective which is emerging. What is emerging is that you have laser weapons. Weapons which can be carried, the laser beams, laser power sources which can be carried on platforms like ship, like the electron laser, or for example, you have the high energy laser sitting on an aircraft, or full capacity fighter carrying a high energy laser and beaming from there. You must have read about the SDI program of the United States of America, which was in the early 80s, where they were trying to have from satellite the laser beams beaming down and killing the objects on the earth. It did not become so successful because of at that point in time, the physics was not so well understood, particularly the interaction of the laser with the atmosphere and so on. But the offshoot of that was that whatever could be done on airborne platforms has been developed. People have understood what are the aero effects, flight, all that has been done. Self-defense with this kind of laser capabilities have been done. So laser system SNTN discipline is a major technology requirement in which laser source first. Now, if I have a chemical laser which occupies a full room, it is of no use to me. So I need to have what is called the fiber optic laser, or a disc laser, or a laser which is going to be occupying smaller space, but can produce almost 100 kilowatts to 500 kilowatts of power. Another important requirement for a laser is the beam control. When it goes into a particular direction, it has a diffraction problem, it has the diffusion problem. So we need to do beam control. Then we should be able to acquire and track the target, and then do power management and thermal management. And we should also know what is the interaction of the laser beam with the material of the target. What kind of physical interaction is taking place? So that requires again material laser interaction physics that has to be understood. So these are some of the major technology areas which needs to be really worked upon to make laser weapons for our armed forces. One of the typical examples which the Americans have done, this is a slide for high energy laser which was put on Boeing aircraft, from where you can have airborne laser. This is the same exercise they did for a space-based laser, or advanced tactical laser, ground-based laser, where basically there is a laser source which is being collimated in that direction. There is a radar kind of a device which acquires the target, and then this laser beam is directed towards this. You can see there is a sensor suite, there is the optical bench, there is the beam director, and the interaction with the target. Now this is what we need to do as far as our Air Force or Army or Navy is concerned. There are another kind of a weapon technology which is called electromagnetic pulse, EMP pulse. When a nuclear explosion takes place, you have an EMP. Now this EMP I can't produce only by nuclear, so I should produce it using high power microwaves. And high power weapon technology is based on pulse power devices which create intense ultra short burst of electrical energy and would be used to power the microwave generator in the HPM weapon. Basically it is called an E-bomb, where you do this kind of a thing by explosively pumped flux compression generator, and this uses a chemical explosive to compress an electrical charge coil. Through that I am able to generate that pump, but merely generating a wave is not enough. I should be able to direct. So you need a director, you need an antenna, and through that you should be able to pass it on in the direction of the target. So that's the technology. People have already done a significant amount of work in this direction. In India also we need to do something to meet the requirements. I saw some of the robots which have been done today in the exhibition, but what is happening in tomorrow's soldiers will be like a predator, remotely controlled reconnaissance and fighter drone, which has the ability to drop things or get things. This was used in Iraq. Swords, miniature combat robots which is equipped with cameras and a machine gun and runs on a caterpillar tracks. This is another thing. You have similarly a gladiator combat robot, which is the modular, allow it to be fitted with the mission specific payloads of the future. This is a kind of a thing. Then you have unmanned fire scout helicopter, you have micro air vehicles, you have unmanned stealth aircrafts, and you have big dog walking robot which will be able to carry all sorts of load. In fact, our own CARE and others have already developed what is called a robotic mule. The miniaturization is taking place to such an extent that there is a nano spy for reconnaissance. It contains nano batteries, motors and communication systems, as well as the video camera payload, and almost like a fly. Can climb and descend vertically, maneuvers using its flapping wings for propulsion and attitude control, and could be deployed to perform reconnaissance, surveillance, and urban environment. The specifications which have been realized already are 16 centimeter wingspan. The weight is only about 19 grams, and speed it can have is almost about 17 kilometers per hour, and have a 3-axis stabilization system. This is a nano spyware. Soldier is also going to be smart. It is not going to remain a soldier as we have today, which is in terms of its uniform will give him the weather protection. It will have its stealth characteristics, can heal them, shield them, and protect them against chemical and biological warfare. Lethality, it should be able to have possibilities of target detection and recognition, identification of friendly and foe, who is friendly and who is not so friendly, and it should be able to do its own target designation. He should have something which I should be able to use a laser beam or a laser range finder or something which will illuminate the target and I can hit them in the night. Survivability, certainly we need to survive, that is protection system, ballistic materials, adaptive materials. The communication network is very important today. C4I, the command, control, communication, computer, reconnaissance, and intelligence, all that put together. He should have a wrist computer. He should have a communicator on his body. He should be able to have a navigation device of its own. He knows his position in real time. Not only that, to his platoon commander, he should be able to talk on real time. So mobility, energy, he should be able to generate power itself. So this is the kind of thing which a soldier as a system we have to provide through the technology which is emerging. And robots will be the fighting units tomorrow. So it's a gun-mounted robo or a smart surface mine robo or a UAV or a communication leader. All this will be, we call them a swarm of robots, which will be doing multiple functions, ground holding, offensive, urban warfare. So they can carry guns, they can carry cameras, they can carry bombs, anything they can have, or even they can have a sniper required for fighting with each other. What is important? Important to hear how a swarm of robots will work in a synergistic manner to optimally to optimize its path of approach to defeat a particular target. That means a lot of descriptive kind of software which needs to be developed in today's parlance using artificial intelligence, behavioral pattern, and so on, to make sure that it is a highly intelligent scenario which will drive the efficiency of the system. Space wars are going to be important. You saw that satellite one boy was doing today. We need that we have sensors in the sky which will monitor what is happening on the ground or in the air. So constellation of IR sensing satellites in GEO and LEO we need. Early warning of the suppose a launch is taking place or an enemy missile is taking. If I have a GEO satellite looking into this, the moment a plume comes out, my IR sensor will pick it up and give me information that from this particular source a missile has taken off. Then I should be able to take care of these kind of missiles which are coming in exo-atmosphere and endo-atmospheric. So need kill vehicles which can be launched using missiles and so on. So this is another technology which needs to be done. As we are going into space, you already heard Mr. Trump talking about creating a space force. Now why he is talking of space force has to be done? Because there is going to be conflict in that space. For why? There are going to be conflict for orbital space, radio frequency spectrum which is going to be utilized by everybody. There is a fixed spectrum, so everybody will fight for it. Technological readiness levels, rapid replacement and capability. Now these are considerations for space, and impact of the space conflict would be, if the conflict takes place, that means you are killing somebody's satellite or you are denying somebody's satellite. That means you are disrupting his communication. You are disrupting his surveillance and intelligence gathering capability. You are disrupting his navigation capability, or he is not able to do what is called the situational awareness on the ground and air using the space object. That means you have whatever space superiority he had, you have denied him. So it will have tremendous impact in the warfare as well as in the civilian time, because we are dependent for our economy of space in a big way. We have today remote sensing satellites, surveillance satellites, which are really telling us how much of the crop has been grown there, how much is the cultivated area, and so on. So this is a major issue of space warfare. And like we have territorial warfare, we have air warfare, so space warfare going to happen. The kind of weapons which will be used in the space warfare are space-based lasers, the space-based interceptors, and maneuverable satellites, a satellite which can be maneuvered as far as the demand is concerned. Now, there are various methods which will be used, like electronic jamming, attacking sensors, and dazzling systems. You will be able to dazzle the satellites. You can throw pallets against another satellite, attack from the ground another anti-satellite system, and so on. So this is the kind of thing that will happen. Solar power has been in the news for many, many years, renewable, but we still have the issues of solar power not available throughout the day. So space solar power is the answer. Dr. Kalam used to take this as a mission. I don't know whether he talked to any one of you in IIT Guwahati whenever he visited, but the fact remains, solar energy is captured in space by large photovoltaic arrays and transmitted via a coherent microwave or laser beam to an earth receiver, where it is converted into a base load electric power, low intensity charging power, or synthetic fuels, and then it is carried forward. Advantage is, solar intensity in the ground is in the space is 1366 watt per meter square, whereas in the ground it is only 1000. There is no night and day, we have 24 hours, and there is no weather loss, and so on. So this has been done many times by many countries from 1970, but because the energy people and the space people don't work together, so it has fallen through the cracks so far. What is the requirement? My requirement is that I should be able to launch large size satellites at a low cost. Today the cost of launching a satellite is almost about $30,000 to $40,000 per kg. Now if it has to be useful in the case of a space solar power, the cost has to come down to something like $500 per kg. And that would need new kind of launch vehicles, what we call as a single stage to orbit, reusable launch vehicles, or two stage to orbits, with increased mass fraction. Today, a typical rocket launch vehicle will not carry more than 3 to 4% of mass fraction. That is, payload is only about that much. We need to go it to about 15%, and that means our engines which we are using today with a high multi-propellants like bipropellants and so on, will have to depend more on the air-breathing engines, and hence air-breathing engines can work only in the atmospheres, but it should be using a specific impulse as high as 1500 seconds. So you need to go for a scramjet kind of a system where you will be traveling at speeds of 6 to 7 or 8 Mach. So these efficiencies have to be increased, and that's a new technology. The materials for aircrafts also are going through a transformation. Nanotechnology is coming up in a big way for both performance enhancement, weight reduction, reduction in flammability levels, development of stealth technologies, and so on. Basically both for noise reduction, thermal flammability, performance improvement. New processes are coming like resin infusion processes and so on, basically to reduce the weight of the structure and also making stealth. Now that is another area which certainly will transform as far as the Air Force is concerned. I mentioned to you about micro-mechanical flying insects. This is another thing like pico satellites which is happening today. Micro vehicle, there is a target. Today there are micro vehicles which are having, for example, 440 grams weight of a micro air vehicle, which can last only for 10 to 15 minutes. And objective is that we should be able to go for 100 grams and a 60-minute kind of a endurance I should have. Different kind of micro air vehicles are under development, and that means that today's nanotechnology, nano propulsion, micro MEMS kind of systems, MEMS actuators, all that will form as part of this. UCAV, that means an aircraft which can carry, unmanned aircraft which can carry rockets and missiles and payloads. That's another technology which is really in demand today. India is also venturing into developing our own UCAV, but I think a lot more is required to be done because it would require control, guidance, navigation, which is done in a not from remote but all on board, and using the today's computing power and today's controls in a miniature manner. All this if we develop, I talked about many technologies, what is the effect it is going to have as far as the nation is concerned? Whether those 9 disruptive, 12, 15 disruptive technologies, or what we talked of defense, or what we talked of precision agriculture and water and security, all that. Some sums have been done. If we converge all this, we can achieve 550 to 1000 billion annual economic impact, which is 20 to 30 times of India's incremental GDP from 15 to 25. Provide 400 million additional people with access to quality healthcare. Have 300 million financially included people. It will provide 14 to 24 million workers more years of education. Achieve 15 to 60% yield improvement for 22 million farmers due to precision agriculture. Save 50 to 95 billion from energy technologies. Gain about 17 to 25 billion dollars from intelligent transportation. And create jobs for 10 million tech-enabled workers in healthcare, education, agriculture, citizen services, and in financial services. So friends, to end, I would like to only say that with this much of advantage, if it is there, obviously we are not going to be the only people to do this. The world is in a race between implementing ever-increasing ways to improve the human condition and the seemingly ever-increasing complexity and scale of global problems. Global collective intelligence, artificial intelligence, and trans-institution can help win the race. For us, that means we need to work together with the industry, with the academia, with the national laboratories, with all of us, bring synergies of action and thought, then only we can win this race of technology development and achieve these frontiers of technology. Thank you very much. God bless you all.